Good day, folks. My name is Ramon Pantin. I am a systems programmer. I have been working in developing operating systems pretty much for my whole professional career. For the last 30 plus years, I've been building operating system kernels, file systems, uh, distributed file systems, distributed job systems, and pretty much anything that makes computer systems work, the software that you don't see that makes your computers, your phones, the servers that provide services to you operate. Uh, I pride in having built and been part of teams that shipped successful products for a large number of companies. And for the last few years, I've been working on a programming language called COOGL, Concurrent Object-Oriented Generic Language, which is a safe programming language meant to solve and to help address the issues that relate to the vast amounts of unsafe system software code that exists out there. Pretty much the whole infrastructure that supports computer systems around the world is written either in C or C++. The deepest, lowest levels of software kernels, the operating systems on your phone, your tablet, your laptop, they're all written in C. The operating systems for the servers that provide services to your computer systems are written in C, other than the mainframe operating systems, which are written in a combination of assembly and PL1 and some other languages. But anything other than the mainframe is written in C or C++. Anyhow, C and C++ are unsafe programming languages, and basically in C and C++ you can under-index or over-index an array. You can dereference memory that's been released. You can dereference memory that's been released and reallocated with a different type. You can do all kinds of operations. You can keep the addresses of variables on the stack that of a function that has returned, and then you can stomp on those variables, and maybe you're stomping on return addresses and whatnot. So C and by inheritance C++ are both unsafe languages in this vast infrastructure of system software that supports pretty much every computer system out there in the world is written in these unsafe languages. The result of this is that programmer bugs that cause these invalid memory references to occur can be exploited by malicious entities or malicious hackers or intelligence services of other countries to penetrate computer systems. Once they have penetrated a program that is under execution, they have taken control of the execution of that program. They can then do other things on behalf of the user that invoked that program, or they can attempt a priority escalation and attempt to take over the kernel that's controlling that operating system itself. Even in large infrastructure, there is the kernel's kernel or the hypervisor that helps implement virtualization, and there's security escalations that can help, through these software bugs, exploit some infrastructure where you're not only taking over one computer system or one virtual machine. You might take over the hypervisor, and you're taking over all of the computer systems, virtual machines that are running under that hypervisor. So basically, we have a vast amount of unsafe system software written in C and C++. This vast amount of system software cannot be rewritten into some of these safe languages that exist, such as Java, C#, Google's Go programming language, or Eiffel. None of these have really, they're not close enough to C in the way that they would need to be to help rewrite that system software. They're all garbage collected, and their type system is incredibly stringent. Their type systems are incredibly stringent, and for the things that C excels at, such as laying out memory to implement network protocols or metadata for file systems or metadata for database systems, those are the areas where these other safe programming languages actually are found lacking, significantly lacking. So this COOGL programming language is both a safe programming language. It is not garbage collected. It's an evolution of the C programming language. It adds object-oriented programming support and generic programming support. Object-oriented programming, as in you can declare classes, You have control of the lifetime of an object. You control the constructor. You can program the constructor, the destructor, the copy constructor for whenever value-like objects are passed by value as arguments, or returned by value by functions, or they're used to initialize some other variables, objects at declaration time. You also have control when an object is assigned to another if it is a value-like object. There is no further operation overloading. You only have control of the object's lifetime. There's, of course, member functions, polymorphism. You can inherit from a concrete class. There's single inheritance, but you can implement multiple interfaces. And the generic programming support is such that when you specify a type as an argument to a generic function or to a generic class, the type argument that you're specifying is type checked against the expected type of the generic function or generic class. So you get your compile errors at compile time, not at link time much later, which is what occurs in C++, where its templates and the arguments to templates, which is the way they implement generic programming, are not type checked at the compilation time. Anyhow, COOGL is incredibly close to C. It has a subset called C lean or clean that is a subset of both C and COOGL. It's C without the preprocessor, without prototypes, without the old Kernighan and Ritchie function declaration style. Only the ANSI C declaration style is supported. And a few minor quirks were also removed from the language. Anyhow, this subset of both C and COOGL can be used to write code that needs to exist and be used on code bases or projects that are compiled both as C and COOGL programs. So from this C lean common subset, then object-oriented support was added in the form of classes. Generic programming was added in the form of generic arguments, where you're passing a type as an argument into a class or a function. Well, of course, safety, which is the most important aspect and the only reason why anybody should entertain yet another C-based object or a base language to be created. So apart from safety, there's a few other miscellaneous additions to the language that makes it easier to program with. There are tuples, principally so that functions can return more than one value. There's array descriptors. So arrays are properly supported in the programming language, whether unidimensional or multidimensional, but array descriptors are key for the safe programming in the language. And the language is incredibly close to C, so you can have projects that are, still using some amount of C code and COOGL code together. Of course, that combination won't be a safe system, but the idea is that you're enabling these systems to be, these large code bases of system software to be incrementally re-engineered into COOGL. The language also has concepts about modularity, so your program is really one or more modules that have been independently developed and compiled, and at the execution time, the main program module it's started, and it might require one or more modules to be loaded at program execution time, and additional modules might be loaded at runtime. Visibility across modules is controlled with the same modifiers that are used to control visibility within classes, which are pub for public, prot for protected, and prib for private, prib for private, which are modifiers that come all the way back from Simula 67, Simula 72. You might recognize them also in C++. Anyhow, the same modifiers are used to control visibility of entities declared in modules and across modules. So an entity that is declared pub is visible across modules. An entity that is declared priv or private is only visible within the file that is declaring those entities. And an entity declared as prot, which is the default if you don't use an accessibility modifier, are only accessible within the module. There's, of course, a notion of namespaces, and that's pretty much the extent of the language. The language is compiled into C11, It is not compiled into machine code so that we can take advantage of existing C compilers. And because some of the pieces of system software that need to be turned into and re-engineered into a safe language are kernels, it's important that these kernels can continue to be built from a COOGL code base translated into C11, and then whatever options are required by the underlying kernel environment, they can be passed to the underlying C11 compiler. There's sometimes special ABI issues or other aspects that are manifested themselves in the native C compiler for the computer system in question. So the programming language compiles into C. C11 is the current target, and it's not used as if it was translating into an assembler that it just happens to be C. The code that you write with all of its indentation and comments and symbol names is preserved and translated so it looks almost identical to what you wrote. Some of the symbol names might have been rewritten, so you might have had a push member function of a stack class, so that is going to have its identifier mangled. That would be the word in C++, but it's not mangled as in you don't recognize the code that it produces. It's mangled as in it gets mapped. So stack dot push, or pushing on a stack object, is really renamed as stack underscore underscore push. We don't allow two underscores in an identifier, and we don't allow underscores at the beginning or at the end of an identifier. So stack underscore underscore push is the identifier mapping for, say, a push member function within stack. There's some other aspects of this identifier mapping, and they're all described in the reference manuals, in the appendixes to the programming language book. At this point, the compiler is being written, is 40% written. There's a book that's been fully written that describes the programming language. It's about 320 some pages. It's 15 chapters, 5 appendixes. The appendixes contain a detailed reference documentation, but the book is pretty much a tutorial in nature, and it describes every aspect of the language, including the C-lean subset of the language. And it has one of the appendixes describes in detail all the differences between C and C-lean. The language was designed with the goal of designing it, implementing it, and being done with it, not for it to become a cottage industry of books about traps and pitfalls and all of the weird things that could happen to you, like the cottage industry that occurred with C++. The language is not meant to be self-ballooning. It's not meant to grow and grow and grow and forever become a thing that swallows more and more programmers and experts into a never-ending evolution of a language that becomes more and more complex. No, the language is meant to be, finished, the compiler to be written, and to pretty much be usable and useful for an extended period of time without any significant evolution on it. My goal is not to remain or be a programming language person. I am a system software person. I would like to use this language to evolve existing system software. One of the other aspects that the language addresses, apart from safety, is what I call the unsafe, undocumented behavior, or they call it undefined behavior, that modern C and C++ compilers believe that anything that is written into the C and C++ standards that say undefined behavior is an opportunity for them to go optimize the code. Undefined behavior was really meant to be where the compiler could, do what is appropriate for the current platform, or if it was too hard, maybe produce a compilation error, or maybe do something that the compiler couldn't do any better. But undefined behavior was not really meant as an opportunity for programming compiler writers to rummage through the standard and find anywhere where it says undefined behavior, try to find code that is undefined behavior, and then optimize it to the point where what you meant to have done doesn't occur. So in a way, the C language and the C++ are degenerating into these pieces of code that, an earlier C compiler would have compiled the code correctly. Nowadays, the newer C compiler might delete some of the code and actually, in a way, introduce backdoors and vulnerability into your code, because the current compiler writers, they're mostly associated with chip vendors, and they measure the quality of their compilers with benchmarks that are sequential benchmarks usually, and they think that obtaining a 1% performance gain, even if they turn a mountain of legacy code into code that no longer works, is something that is worth pursuing. Of course, they cannot go and break every code base out there, so they do provide options to disable some of the most egregious optimizations. Anyhow, more about this is in the book. Anyhow, the goal of the COOGL programming language is to help rewrite these huge and re-engineer these huge code bases from C into COOGL. It's not really a rewrite because the two languages are extremely close to each other. So it's more retarget, or do some amount of re-engineering. It's meant to be forever a free programming language with an open source compiler, and with a book that describes a programming language that is also free. You can download the PDF for the book and read it, provide any feedback that you want, and tell us what you think. But the idea is that this is not an effort to make money. This is an effort to provide a tool that is sorely needed so that we can begin to re-engineer these systems into safe systems, so that humanity is not at risk from malicious entities and cyber warfare and hackers from continuing to invade our computer systems. Remember, your phones, your tablets, your laptops, and the servers that serve you and that store your information, they're all written in these unsafe languages, and something needs to be done about it. None of those code bases are going to be re-engineered into Java, into C#, into Eiffel, or into the Go programming language. There's some other interesting languages out there. Rust is a compiled language that is being used by the Mozilla Foundation to re-engineer their browser, so that it's that part of Firefox that is being written in Rust is safe from the programming language perspective. Anyhow, Rust is incredibly different syntactically and very far away from C, so it's not a good language to incrementally re-engineer something like the whole Linux kernel, or a whole BSD kernel, or AIX, or Solaris, or some other operating system, Windows NT. I guess we call it Windows NT. What is modern day Windows? So any of those kernels and operating systems and device drivers and file system frameworks and file systems and networking code would be much more easily rewritten into COOGL than into any of these other languages. COOGL preserves the facility that C has to allow you to lay out network protocol packets with headers, optional headers, variable length, payloads, footers, and send them over the network, and you code that exactly as you would code it in C, but it is safe. And the same if you were laying out metadata or some other database data that describes layouts that exist on disk, and you're going to store that metadata out into some storage system, or maybe some well-documented format that some processes are using to communicate through shared memory. So when you really need to control the external layout of memory, which is one of the areas where C shines, and of course C++ inherited that, then you really want to do things how C does them. Now, you want to do that in a safe way. Now, COOGL is a programming language. We have 40% of the compiler written. The book is, you could say, almost in a final, ready-to-publish state. The compiler is, the grammar for the language is context-free. Means you can parse it without the aid of a symbol table. C is not a context-free language, by the way. You need to have a symbol table because any type declared with a typedef will lead to ambiguities in the parsing unless you're looking up in the symbol table at the time of parsing to know what an entity is or is not. More of that is described in the book. Anyhow, so we're looking to raise funds to support an engineer full-time from here to November to finish with the code generation parts of the compiler and to help with the testing. Pretty much all of the effort up till this point has been bankrolled by myself, and it's been mostly an effort that I have started and I have worked on as a hobby or pastime for quite a few years now. At this point, I have a volunteer that is going to work for free, a computer science student, editing the book from the English language perspective, just to make sure it's beautifully written, and whatever areas of the book are confusing or need to be polished from the English perspective, it will be done by this person who is also a writer. So it's a computer science / writer person that will wordsmith the book to bring it into even better quality than it currently it is at. Being a computer science student, this person is also going to be a guinea pig for seeing if this book is good enough for anybody to understand the language from no knowledge of it. So we're looking to fund one more engineer. I am working on this still at part-time. I have full-time work in the startup that I've been working on for the last 2.5 years, and I don't have enough cycles to complete the compiler. I would want to see the compiler being finished. I'll work on it as much as I can, but I need to fund a second engineer to help finish the compiler. The state of the compiler is that there is a token specification file, there's a grammar specification file. These two specification files, which are very clean, are run through some scripts which produce Bison parser and a Flex lexicographical analyzer. Bison and Flex are the equivalents, the open source equivalents of Jack and Lex, the classical Unix tools to generate compilers. Anyhow, this Bison grammar that is generated from the grammar specification also is generated with the actions that help, but that build from scratch the parse tree. And this parse tree is, it also generates various methods to dump the parse tree, to insert symbols when they're declared into symbol tables, to introduce symbol tables in all of the places where a new symbol table needs to be introduced. So wherever any of these rules opens a new scope, the scripts cause that the code generated for those actions to create a symbol table, and then subsequent declarations within that scope go into the symbol table. So the generated compiler also has code to prune the parse tree, so it becomes more of an abstract syntax tree, in the sense that if you have something, for example, an expression a plus b, the parse tree or the abstract syntax tree for that is really a node that represents the plus operator, another node that represents A, and another node that represents B, without all of the artifacts that would have been there in a parse tree for all of the intermediate rules and alternatives that parse an expression into such a simple expression such as A plus B. There's a pass on the parse tree that turns it into this abstract syntax tree, which basically prunes all of these extraneous rules. There's also generated code that translates lists. For example, if you have an array initializer with many, many initializers, that would be a very long list, one element per list entry in this array initializer. And if you're walking the parse tree and going recursively down an array initializer, well, that consumes a lot of stack for the compiler. So all of these lists are translated by this generated code into tables, so they're walked as arrays within the compiler as opposed to being walked recursively, which makes makes the compiler not to require as much as stack depth. The compiled code is meant to be as close as possible to the code you wrote, so we preserve the indentation, we preserve the comments, and wherever the code doesn't need to be affected at all, you might have a local variable within a for, with an I++ or something, none of that is going to change. It's going to look identically to the code that you wrote. But, in the generated code, there will be calls to constructors, destructors, copy constructors, and whatnot. Calls to member functions, you will see the dispatch through the polymorphism mechanism and whatnot. But, again, we're looking to fund one engineer from here to November, and to complete the compiler and have an initial version of the compiler the compiler available. You could call it, a late beta level compiler. There's an extensive test suite that is being used at this time to test that the syntax of the compiler is indeed accepting the programs that we expect it to accept. And what else? So any feedback that you have about the programming language, you can download the book, read it, send us feedback about what parts are not easy to understand, what needs better explanations, what parts of the language you think might have a design flaw. And any and all feedback would be incredibly valuable for us. We also would like to have your support. We would like for you to make any contribution that you can from $5 and up. There's various rewards, including a printed hard copy, autographed versions of the book at various levels. There's also nonprofit sponsorships and corporate sponsorships that would involve, if the entity that is providing the sponsorship so desires, a lecture, an in-person lecture by myself about programming language with a large number of autographed books for the audience as well. Anyhow, we'd love to finish this effort. We put a lot of love and energy, and time is money, a lot of personal time into it. And we would really, really appreciate your support, and I hope that you have a wonderful day. Thank you.